Hello everyone, in this video I'm going to talk about differentiation for functions of many variables. I'm going to discuss how to compute partial derivatives so that we can compute the total derivative of a function of many variables. As I assume most of you know, a differentiation is a concept which involves the approximation of a function near a given point by a linear or affine function. This is essentially the main idea of calculus, that you can break complicated functions which are maybe their graphs are curving and so on, and you can approximate it locally by flat things. And you can kind of add all the flat things together and understand very well what the function's doing, because we can compute integrals and so on for the flat objects. So near each point, we're going to need to find a linear approximation of a function. So in this video, we're going to introduce this concept. We're going to discuss what the derivative should mean, and we're going to learn how to compute it, and how to compute things like tangent planes to the graphs of a function of many variables. First, let's talk about what differentiation means in the single variable case, just as a review. So this is a little cartoon here. This pink curve is the graph of some function f of x. This down here is the x-axis, and we're going to zoom in near this point x naught. Okay, so if we sort of zoom in on the graph, and I drew this graph to be a very smooth looking graph. So if we blow up the graph near this point x and we come over here to this picture, this point x naught, we see that this graph, this pink graph of f here is close to this straight red line, much closer than it looked in this global picture here. In this picture, this straight red line deviated a lot from the pink curve as you moved away from x naught. But we see as we zoom in, the error in this affine approximation, which is represented by this purple region here, this error becomes small. And it's not just small because we're zooming in and the whole box is small. It's small even relative to the scale. So what we mean is that as this box of size h becomes small, this purple area here is much smaller even than h. So if we divided by h, the size of the box, the error here would still go to 0. Okay, so we say that this is what it means to have a good linear approximation. It means that when you zoom in and you blow up the picture, you're becoming flat. So the slope of this red line here is the derivative of the function f at the point x naught, written f prime of x naught. And the equation of the line is, well, it's the slope times x minus x naught. I'm just writing the equation of the line in point slope form. So it's the derivative f prime of x naught times x minus x naught plus f of x naught, because it has to go through this point. Okay, so this red line has that slope. And so we should define derivative to mean that the error, this purple, the size of this purple region here, which is f of x minus L of x, that go to 0 faster than h. So maybe when we divide by h, that goes to 0. So that gives us the notion of derivative. So we see that the error in the affine approximation is f of x minus L of x. We can write that out like this. F of x minus, in parentheses, f prime of x naught times x minus x naught plus f of x naught. Okay, so now let's make a definition. We say that f, a function from R to R, is differentiable at the point x naught if there exists some real number a naught such that this limit is 0. All I've done is basically translate this error down here and divide it by h, which is the size of the window. And then I take the max over all points in that little window. Okay, so this number here, before I divide by h, represents the longest sort of purple vertical line segment here. So in this case, it would be one of these points on the very edge. Okay, and if we divide by h, then we're saying we're just measuring the ratio between that maximum distance here and the size of the whole square. And I think you would agree that if something's a good linear approximation, then this distance should go to 0 relative to the whole distance of the square. Okay, so that's what it means to be derivative. If we can find such a number a0, then we call a0 the derivative of f at x and write a0 equals f prime of x at x0. Okay, this is not the way the derivative is usually written, but it's equivalent. So it's nice to see it written like this. Of course, if there is one a0, then it's unique, and that's why we can write it in that notation with the f prime of x0. Okay. And if you are used to seeing the derivative of a function of a single variable written in a bit of a different way, with a formula that looks like f prime of x0 equals limit some h goes to 0, blah, 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 then you can take this definition and slowly translate it into and see that your old definition is equivalent. Okay. For instance, I could take this point here. Actually, this is a mistake. Let me point this out. This should be a plus. I forgot to take that plus. Okay, now it's better. So you could take this minus sign with this and group it with the f. Then you could divide by x minus x0, which is kind of proportional to h, and you would get f of x minus f of x0 divided by this equals a0. So you can, if you want to, you can experiment with rewriting it. But this is what it means to have a derivative. It means that I can find an affine approximation, so I can find a line basically, so that as I zoom in, my function is getting, its graph is getting closer and closer to that line in this exact precise sense. Okay. So now this is the reason that I use this definition, which is less standard, although equivalent, is because it generalizes to the case of many variables very easily. So let's discuss what differentiation means in the multivariable case. And before we can get into this, because I'm going to generalize the definition of the single variable case that I just gave, we need to discuss what a linear or affine function even is in multivariables. Okay, so this is what it is. If I have a function L, which depends on n variables, and I need to spit out a function of m variables, okay, then what else could affine be if not this? It just means that, say, the first coordinate of the output has to be some slope, a11 times x1, plus some other slope for x2, and so on. Each variable gets its own slope. Okay, so you write this. And of course you have another free variable here, which changes the height of the graph. Okay, so the first coordinate looks linear like that, the first coordinate of the output. And then of course every output gets its own sort of linear function here. And the quote-unquote slopes now are here. So the first variable gets a different slope in the second line for the second variable of the output. And so you sort of have this idea of quote-unquote slope for every input variable and every output variable. So it makes a matrix. Okay? It makes an m by n matrix because there's one number for every input-output combination. Okay? So I can list them as a column vector like this if I don't want. So here I've written x1 comma dot 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 comma xn, but I'm going to just write the output as a column vector. Okay, and if I did write the input as a column vector as well, then I could write this whole thing as matrix multiplication. So I have a matrix capital A, which is the matrix of all these things I'm calling slopes. I have some vector b1 through bm. My matrix is not square because there could be, because f is a function from Rn to Rm. So A will be a matrix which is m by n. Okay, it's going to have m rows because there's m outputs. All right, so A is m by n. All right, And so a linear function, or an affine function, which goes from Rn to Rm, is just something of this form. It's a matrix, which is m by n, times the input vector, plus a fixed vector. Okay, notice that this vector is in Rn, and this vector is in Rm, because this matrix is m by n, and this in an m by n matrix by an n by 1 vector gives me an m by 1 vector to match this. All right, so this is what an affine function is in many variables. So how are we going to define the derivative of a function of many variables? Well, we're going to say that I can approximate the function locally by one of these. So let's see the definition. Okay, so if you're not watching closely, you may not even see a change, because I'm using these absolute value bars again. Now, of course, it means Euclidean distance, or Euclidean length of the vector, instead of just the absolute value. And here I'm not saying it, but this is matrix multiplication here. Okay, but it looks just like the multiplication I had before. And so we sort of hide in the notation all the extra variables. So let's suppose that the domain is U. U is a subset of Rn, some open set. And f is a function from U to Rm. And I was going to say x naught is a point in U. Okay, so I take some point in my domain. All right, so we say that f is differentiable at x naught if there exists an m by n matrix A naught, a capital A naught, such that this limit holds. And I have another mistake. Because of the way that I'm writing this, I should write this limit as h goes to 0. Okay, so this limit is exactly the same as I had before. It's just that the multiplications are of matrices here. So this is an m by n matrix. This is again a vector in Rn. So m by n times n is m. And this is in Rm, and this is in Rm. So everything matches up. This absolute value here is happening in Rm. It's the Euclidean distance in Rm. Okay, we max over all the points x in the ball of radius h centered at x naught in Rn. And we divide by h. Okay, so implicitly the Euclidean distance in Rn is involved in this. The Euclidean distance in Rm is involved in this. I have matrix multiplication here. I'm adding vectors in Rn. But otherwise, the definition is exactly the same as it was in R1. Okay, so I want f to be approximated by this affine function. And this matrix A naught is the derivative of f. We call it the total derivative of f. And we use the notation df at x naught. We only use the prime notation for functions of a single variable. For functions of many variables, we use df. Okay? All right. Let's talk about what happens in the case when the target is one-dimensional. So m equals 1. Okay, so we're talking about the gradient of a scalar-valued function. Scalar-valued. So here this is r, m equals 1. In this case, A naught is a 1 by n matrix, 1 row in columns. So it's a row vector. Okay, and if you do matrix multiplication of a row vector by a column vector, you get a 1 by 1 matrix that is a number. And that number is actually the dot product of these two vectors. So this thing is called a row vector, because when you write a 1 by n matrix, it's just a row. And this thing is a column vector. And a row vector times a column vector is just the dot product. Okay, so we can change the notation slightly, and instead of thinking of that capital A naught matrix, we can think of, because now my matrix is just going to be a row vector, we can think about it as a vector in our n. And we can call it the gradient vector. So for a scalar valued function, we don't speak of the total derivative, we speak of the gradient. Okay. And we don't use D, we use this nabla symbol here. This triangle, it's called nabla. Okay, so nabla f of x naught, or some people would say grad f of x naught, or just gradient. All right, so what does it say in this case? Just writing the definition again, and again I have written this limit badly, so let me fix it. Okay, so here it's again the same limit. The limit as h goes to 0, 1 divided by h, because I have to divide by the window size. Take the max of all points in the ball of radius h centered at x naught, of the difference between f of x and the linear approximation at x. Okay, now here the linear approximation has a dot product here, so it's just this vector p naught dot x minus x naught plus f of x naught, so that it goes through that point. Okay, and you'll recognize this because it's scalar valued as the equation of a plane. The graph of this function will be a plane in dimensions n plus 1. Okay, and that's why we speak of the tangent plane to a scalar valued function. The tangent plane to f at x naught is the graph of the linear approximation. This function in blue is called the linear approximation. Okay, it's important to understand just the scalar case m equals 1, because it may seem like a special case, but actually it basically contains everything, because you can view the case, if I had a general m here, as just a list of f's, f1, f2, ... fm, and each of these is scalar valued. So if we can understand the scalar valued case, then we can understand the general case, as I'll explain in just a second. So let's talk about how to compute the matrix. How do we actually compute it? This matrix df of x naught, the total derivative. So again, I'm going to talk first about the case m equals 1, the scalar case. In this case, this thing, like I said, is just a gradient vector. And let me tell you how to compute the gradient vector. Okay, the gradient vector is the list partial f with respect to x1, or the partial derivative of f with respect to x1, then the partial derivative of f with respect to x2 at x, ... the partial derivative of f with respect to xn. Okay, this symbol here is called del. It's written like this curly. It's supposed to remind you of df dx. But because our function depends on many variables, we don't want to use this notation. So this symbol, which looks like it, is used instead to remind you that it's a function of many variables. This is called a partial derivative, and I'm going to tell you how to compute it. But if you can compute a partial derivative, then the gradient is just the list of partial derivatives with respect to each of the coordinate directions. Okay, here I'm thinking of x as being in the coordinates x1 through xn. So these are the coordinates. Okay? And partial f with respect to xk is the partial derivative with respect to in the xk direction. And what is it? Well, it's just the usual single variable derivative of f as a function of xk only. Okay, so what you do is you imagine that all the variables except for xk are frozen at the coordinates of this point x. And you vary just the xk coordinate. Now you have a function of only one variable, only just xk. So you can take its derivative like you already know how to do in the single variable case. Okay, and you get something, assuming it's differentiable, as a function of just that coordinate. And if it is, then the derivative is defined to be the partial derivative of f with respect to xk. Okay, so this is what a partial derivative is. Partial derivative of f with respect to xk is just the usual single variable derivative of f as a function of xk only. Okay, so if you wanted to write it down, you would see that you have, again, limit h goes to 0 of 1 divided by h. And here you're just taking the maximum of y in this interval. So now y is just a real number in this interval from xk minus h to xk plus h. That's the ball centered at xk of radius h in only one dimension. It's just an interval. I could make it open or closed. It doesn't really matter. If I write max, I guess I should have all of these sets closed. But in any case, so what do? You take f of the coordinates of x, the point whose derivative you're trying to define, and you go x1 through xk minus 1, and then you plug in y for the k variable, and then you continue with the other variables. Okay, so you're thinking of this as kind of, f tilde of y if you want. The other variables are frozen. And you want this to be the slope of the line, ak, and then you do ak times y minus xk, just like you would in the single variable case. And then you subtract just f of x. So I just wrote f of x with all its coordinates here, so you could compare to this one. But this is really just f of x. Okay, so I'm only allowing one coordinate to vary. This is identical to the single variable derivative. Okay, and if this limit is 0 equals 0, then it tells us that ak, the slope in here, is equal to the derivative of f with respect to xk. So that's how we compute it. Let's see an example. Now I have a function in 3 variables. F goes from R3 to R. And I want to compute the gradient of f. So it's equal to x squared y plus z sine x. Okay, so the gradient of f at the point x, y, z is, okay, so first is the partial derivative of f with respect to x1, or x. Here I'm using x, y, z instead of x1, x2, x3. So it's the partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z. Okay, of course, at the point x, y, z. So maybe here I'll suppress the arguments. Okay, so I want to compute each of these now. Let's compute the partial derivative of f with respect to x at the point x, y, z. What do I get? Well, I just pretend that y and z are constants, and I just differentiate in x. So I get, for this term, I get 2xy, because the derivative of x squared is 2x, and I'm just multiplying by y. And the derivative of sine is cosine, so I get plus z cosine x. Okay, let's take the derivative of f with respect to y now. Okay, we see that the second one does not even depend on y, so its derivative will be 0. And here I just have y, it's linear in y, so the derivative is just x squared. Finally, I'm going to have the derivative of f with respect to z. And again, there's only one z in there, and it's linear in z. So what's the slope? It's x squared, it's sine x. So I get sine x. Okay, so the gradient at the point x, y, z is simply 2xy plus z cosine x, comma x squared, comma sine x. Oops. Let me move this over. Okay. Okay, let's do another example. Let's find the equation of the tangent plane to this function, the same function I had before, at this particular point. Okay, so what I should do is I should compute the gradient of f at that point. And let's remember from the last slide what the gradient of f was. It was 2xy plus z cosine x, x sine x. Oops, no, x squared sine x. Okay, and now let's compute the gradient of f at that point, pi 1 minus 1. So what do I get? Let's see, when I plug in x equals pi, y equals 1 to the first term, I get 2 pi. And then I get z cosine x. When x is pi, cosine is minus 1. So I get minus 1 times minus 1, which is plus 1. X squared is pi squared. And sine x is 0 when x is pi. Okay, so this is the gradient. So the slope of the tangent line, or the I should say the normal derivative of the tangent plane is equal to the gradient. Okay, or I can just, another way to say it is, what's the linear approximation? Well, the linear approximation is just L of x, y, z equals the gradient of f at this point, dot x, y, z. Just a second, this is a mistake. Let me move this down. Okay, so I'm gonna write it like this. L of x, y, z equals 2 pi plus 1 pi squared 0. And then I'm going to have x minus this point, x, y, z minus this point. So I'm going to have x minus pi, y minus 1, z plus 1. This is a dot product, plus the value of f when I plug in that point. Okay, and the value of f is pi squared times 1 minus, or plus z, but z is minus 1, times sine x, which is 0. Okay, so I get pi squared. So this is the linear approximation. Okay, so the equation of the tangent plane is w, which is maybe the fourth variable in R4, equals L of x, y, z. Okay, so if I look at all the points x, y, z, w in R4, then I will have a flat plane-like thing, which is tangent to the graph of f. The graph of f is something in R4. Okay, so I won't write all of this out because I'm running out of room on the slide. But if you wrote all that out and you expanded it, you would have a nice equation for the tangent plane. Next, we're going to talk about computing the total derivative, capital df of x, of a function from Rn to Rm. Okay, so in the general case, when the target space can be m-dimensional, as I said before, I can think of f as just a list of scalar valued functions, f1 dot 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 fm, where each of these fj's, again, is scalar valued. So here's how you make the total derivative matrix. You compute the derivative, the gradient, of every fj, and you write it as the jth row in the matrix. Okay, there's m of these, so you're going to get m rows. That's how you remember that these gradients get stretched out into the rows. And each of these gradients is something that lives in Rn, and therefore there's n entries in each row. So there's n columns. So if you wrote it out, you would see that the gradient of the first scalar valued function f1, written as a row, is just partial derivative of f1 with respect to each of the variables. So as you go this way, the variables are increasing. Okay, but the index on the f remains the same. And as you go down, you see you get the variables are constant, but the index on the f is increasing. Okay, so the ijth entry of this matrix is just partial fi partial xj. This is the total derivative's ijth entry. Right, because the rows, the second row is the index on the f. If this index on the f is 2, then you're in the second row. So the rows here correspond to the f. Okay, so that's it. That's all the total derivative is. Let's have an example. Let's compute the linear approximation of this function, which is a function of two variables, and it outputs two variables. So f is going from R2 to R2. So the linear approximation should involve a 2x2 matrix. So let's compute it. Okay, so first I need to compute the total derivative of f. Let me write f like this, as f1 and then f2, where f1 of xy is just the scalar valued function y squared x plus sine x, and f2 is just y minus x squared. So these are pretty simple functions overall. Now I'm going to compute the gradient of f1 and the gradient of f2. So the gradient of f1 is, okay, so I should compute the partial derivative with respect to x first. So I get y squared plus cosine x, because the derivative of this is with respect to x is y squared, and the derivative of this is cosine x. Okay, and for the derivative with respect to y, I get 2xy, because the derivative of y squared is 2y, and x is just a constant we're imagining. And let's compute the gradient of x, of f2. Okay, here y and x are kind of just separate. It's just a function of y plus a function of x, so it's easier to compute. So when I compute the derivative with respect to x, I get minus 2x. And when I compute the derivative with respect to y, I get 1. Okay, so now I can write down the total derivative matrix. df of xy is the following 2x2 matrix. Okay, so I get y squared plus cosine x, 2xy. I'm putting the gradients of the functions as rows, minus 2x, 1. Okay, so this is my total derivative matrix. I'm going to erase the work I did here to give myself some room on the blackboard. But I'm going to keep this total derivative matrix that I computed. Okay. Let's see. What should I do next? So the linear approximation is going to be L of xy equals, so I'm going to have the matrix df at the point, so pi over 2, 1. And then as a column vector, I'm going to have x minus pi over 2. y minus 1. So the matrix times x minus x naught, where x naught is this given point here. And then I should subtract as a column the value of f at that point. Let's compute the value of f at that point. So I plug in x equals pi over 2. That makes sine x equal to 1. So I get pi over 2 plus 1. If I computed that correctly. And for the second point, I get 1 minus pi squared over 4. Okay, so now let's just write this in a nicer way. Let's plug in the values here. Plug in this point into this matrix, and so I can have something more explicit. Okay, so I'm going to have a 2 by 2 matrix. The first point, let's see, I'm going to plug in pi over 2 and 1. Pi over 2 for x makes cosine 0. And then 1, I get 1. So the first entry is 1. This entry over here, 2xy, is just going to be pi. 2 times pi over 2 times 1. Then I have minus 2x, so I have minus pi. And I have 1. So I have a nice looking matrix, in fact. Not bad, because I just made up this problem. All right, so I can simplify this more if I want by actually doing this matrix multiplication out. I'm not sure if it's going to lead to an expression that looks any nicer, to be honest with you, so I'm just going to leave it like this. But this is the linear approximation of my f as a function of x and y. You plug in x and y in here, then you multiply everything out, and you'll get a column vector with 2 entries, which is the output. All right. Let me tell you some basic facts that you should know about differentiation and partial derivatives, just as a caution. So, and this is something that's different from the case of functions of a single variable. If you have a function of a single variable, then if the derivative exists, then it's differentiable. In the sense that you just compute, and if you can show that the derivative exists, then you say that f is differentiable. Here, if you can compute all the partial derivatives and show they exist, it doesn't mean that f is differentiable. Okay? So just because they exist, you cannot go back this way. It's not true. If they exist and the partial derivatives are continuous in a neighborhood of your point, in an open ball centered at your point, then you can say that f is differentiable. Okay? And if f is differentiable, then you can say the partial derivatives exist. So if you're in this box, you can jump to the other box. Okay, but you cannot go back. This is not true. Okay, so if f is differentiable, you do know the partial derivatives exist, but you don't necessarily know they're continuous in a neighborhood of your point. Okay, so you can always go this way, but you can't go back. If you're in the case of the first box here, then we say that f is C1 in a neighborhood of the point. Okay, so if the partial derivatives exist and they're continuous, then we say the function is C1. Okay, so C1 implies that you're differentiable. A differentiable implies that the partial derivatives exist, but you can't go back the other way. The reason for that is that you can have that the partial derivatives exist in the coordinate directions, but maybe they don't exist in some other direction. So let me try to explain with a picture. So imagine that this is R2. Okay, and you have a function. Oops. This is R2, and maybe you are mapping into just to the real line. Okay, so it's just a scalar valued function. Okay, your f. And I'm going to define an f, which definitely has its partial derivatives existing. Because what I'm going to do is I'm going to say that f of x and y equals 0 if either x or y is 0, or both. Okay, so I'm just basically saying that I want my function to vanish on these axes. Okay, and then I'm just going to say make this be anything you want. So just any function you like. Elsewhere. So off the coordinate axis, just pick this to be whatever function you like. I don't care. The point that I'm going to make is that at the origin, the partial derivatives of f exist. Because if I'm standing at the origin, let's say that I freeze the x value to be 0, and I let y vary. Well, as I vary, I just move up and down on this coordinate axis, and I see that f is always 0. So the affine approximation by the 0 function works just fine. Okay. Likewise, if I vary the x and keep the y frozen, I just get 0. And so the partial derivatives exist and they are 0. But because I'm allowed to make the function be whatever I want inside of here, away from the coordinate axis, I can make it be a terrible function that does some crazy things, just whatever I like. And then if I try to approximate that function in a whole neighborhood of the origin, not just on the coordinate axis, by a linear function, it'll be impossible. Okay, I could even make f have a jump discontinuity across here. I can make it be 17 here, 8 here, 6 here, and 3 here, and then 0 on the coordinate axis. The partial derivatives exist, but if I try to approximate that function by an affine in this ball, you'll see there's no way that you can do it. So that's why you can't go back this way. Okay, now you'll see that the partial derivatives of that crazy function that I just made actually exist. So where do they exist? Well, they exist at the origin, and they exist every point inside, because every point inside the one of these quarter spaces is going to have derivative 0. Okay, but the partial derivatives don't exist on the coordinate axis away from the origin, because at this point the derivative in the x direction won't exist, and at this point the derivative in the y direction won't exist. Here I'm just imagining here that I have 17, 6, 3, and 8 or something. So I have a jump discontinuity here as I vary the function in this direction. So the derivatives won't exist. Okay? So you see that I have partial derivatives existing, but I don't have that partial derivatives exist and are continuous in a neighborhood of the origin. And so that's the reason that I can fail to be differentiable. All right, so that's all that I wanted to say about differentiability of functions of many variables, at least in this lecture. I'll have more to say about it in the next lecture when we talk about curves and the tangent to curves.